Imagine an AI system that gets stuck on a problem. And so it decides to just, pause, open up its own underlying code, and rewrite its operating system to solve it.
Right.
Which, I mean, it sounds like a scene from a science fiction movie right before everything goes terribly wrong.
Yeah, exactly.
But as of right now, in labs around the world, this is actually happening. Today, we are looking at the invisible scaffolding that that makes this possible.
It is a massive shift in how we build these systems. Because for years, the entire tech industry has been, well, they've been obsessed with the engine, right?
Oh, for sure.
We look at the sheer horsepower of a new large language model, the billions of parameters, the raw compute that goes into training it. But a powerful engine just sitting on the asphalt doesn't really do you much good.
No, not at all.
You can't just drop a V8 engine on the highway and expect it to drive you to the grocery store.
Right, because it needs a steering wheel, it needs a GPS, it needs pedals. And in the AI world, we call that the harness. It's this complex layer of software sitting around the raw language model. And the harness manages its memory, it orchestrates its tool use, routes its workflows, and decides what it actually pays attention to.
Yeah.
It's the thing that turns a static chatbot, where you type a prompt and get a text response, into an autonomous agent that can actually go out, navigate the web, use APIs, and get things done.
And our goal today is to synthesize the most critical insights from a stack of 5 cutting-edge research papers that are entirely focused on this massive concept of agent harnesses.
Yeah, we've got a lot to cover.
We do. So whether you are prepping for a high-level tech strategy meeting tomorrow, or you're just, insanely curious about where AI is heading next, understanding the harness is essentially the shortcut to understanding how AI truly operates in the real world right now.
Because the model might be the brain, but the harness is the nervous system and the hands.
That is a perfect way to put it.
Okay, let's unpack this. We have our car engine, and we have our harness acting as the rest of the car.
But if the harness is the car, that naturally leads to this wild thought. Can the AI build its own car?
Right.
Can these foundational models autonomously write and improve their own scaffolding without human engineers holding their hands?
That is the exact premise of a really fascinating piece of research we are looking at today, called SWE-bench.
SWE-bench.
Okay, so the researchers wanted to see if modern foundational models possess the intrinsic capability to act as their own autonomous systems engineers.
Wow.
So they set up a controlled testing environment, taking 9 different models and giving them a basic, just a seed harness.
Like a starter kit.
Exactly, a starter kit. Then they tasked them with evolving that harness across domains like web search, complex office tasks, and, general agent activities.
So they basically said, here's a starter kit, go make it better.
Yeah.
How did they actually do it? I mean, what did the AI build?
Well, the top performing models, specifically GPT 5.6, Sol, and Claude Opus 4.8, they achieved massive gains.
We are talking up to a 16.6 point absolute improvement over the baseline seed harness.
That sounds like a lot.
It is. To put that in perspective on these complex benchmarking tests, a 16-point jump is the difference between an AI failing to complete a basic multi-step web search and an AI performing at the level of a custom-built state-of-the-art harness that took human engineers months to design.
Well, okay, give me a concrete example of what it actually changed. If it's writing its own code, what does that code look like?
Yeah, so one of the most impressive examples came from GPT 5.6 Sol. On its own, it identified that it was struggling with web navigation.
Okay.
Because modern websites are full of HTML junk ads, trackers, formatting tags, and all that just overwhelms its context window.
Oh, right. It gets distracted by the code of the website itself.
Exactly. So the model autonomously engineered a specialized web page cleaner.
No way.
Yes, it wrote a Python script into its own harness that scripted away all the visual and formatting noise from the HTML. But crucially, it preserved the raw text and the hyperlink structures.
So it basically built itself an ad blocker and a text extractor just so it could read the web more efficiently.
Yes, exactly. And it didn't even stop there. It also built a hierarchical router.
A what?
A hierarchical router. So instead of trying to hold all of its available tools in its active memory at once, which is incredibly inefficient, it organized its tools into categories.
Oh, I see.
If it knew it was doing a math problem, it routed itself to the math tools and just ignored the web browsers entirely. It engineered a more efficient way to think.
That is incredible, but also slightly concerning. I mean, if it can write its own code to make itself better at writing code, does it just keep getting better forever, or is there a catch?
Well, there is a ceiling, and it brings this right back down to reality. What's fascinating here is that the research found two major catches.
Okay.
The first is a phenomenon they call early saturation. You might expect a slow, steady climb in improvement, where the AI just keeps iterating toward perfection.
Right, like a learning curve.
Yeah, but instead, models hit their peak performance quite early in the evolution process. They quickly discover really brilliant high-quality structures, like that HTML cleaner.
Mm-hmm.
But as they keep tinkering, they start introducing detrimental modifications. They over-engineer it, break things that were working beautifully, and the overall performance actually drops.
So they act like the classic developer who just doesn't know when to step away from the keyboard.
Yes, exactly.
The code works, but they just have to refactor it one more time until the whole system crashes.
It's a total lack of goal-oriented persistence.
Yeah.
A human engineer knows when a feature is done and it's time to move on.
Yeah.
The language model just sees an instruction to optimize.
Mm-hmm.
So it optimizes until it ruins it.
That's hilarious, actually.
Until you look at the second catch, which is the financial cost.
Mm.
Running this autonomous evolution process is wildly expensive.
Oh, of course.
To get that top-tier performance from GPT 5.6 Sol, it cost over $500 per single run of the evolution process.
Wait, $500 just to optimize the harness for one specific task? I mean, for enterprise companies doing millions of tasks, that math does not work at all.
It really doesn't. But the paper did highlight some incredible efficiency on the other end of the spectrum.
Oh, yeah.
Models like DeepSeek V4 Pro managed to synthesize functional harness improvements for less than $1.
Less than $1. Wow.
And Twin 3.7 Max delivered formidable performance for under $40. So there's a massive logarithmic trade-off between how much money you throw at the problem and the evolutionary capability you get out of it.
Okay, I want to go back to that first catch, though, where the AI over-engineers things and breaks its own code.
Sure.
Because that sounds like a massive stability issue. If an agent is constantly rewriting its own operating system based on the very last thing it failed at, wouldn't it constantly break old features just to fix new ones?
That is a critical bottleneck. And actually, it is the entire focus of another paper we are looking at in this deep dive called Harness Continual Learning, or HCL.
HCL, okay.
They coined a term for this exact problem. They call it harness level forgetting.
Harness level forgetting.
Yeah. Let's say your agent updates its memory retrieval system to get better at searching the web for modern pop culture facts. It rewrites a routing rule to prioritize recency.
Makes sense.
But by changing that rule in the harness, it inadvertently ruins its ability to retrieve historical financial data that it used to pull perfectly.
So it's like fixing the brakes on your car, but accidentally rewiring the radio to honk the horn.
That's a great way to look at it.
Fixing a web search tool might break a previously perfect email workflow.
Exactly. The components of a harness, the memory, the tool registries, the routing rules, they are tightly coupled.
Right.
The underlying foundation model hasn't changed at all. Its neural network parameters are frozen. But because the harness changed, the agent forgot how to do something it previously mastered.
Oh.
If it just pushes code updates straight to production based on its most recent failure, it causes catastrophic interference across other tasks.
So how do we stop the AI from constantly breaking its own radio, to use the analogy? Like, how do we let it evolve safely?
Well, the HCL paper proposes a framework called guarded harness evolution.
Guarded harness evolution.
Right. Instead of a single AI agent just overwriting its own code on the fly, they split the system into two modules, a continual optimizer and a continual evaluator.
Okay.
The optimizer looks at recent failures and proposes candidate changes to the harness. But those changes are kept completely isolated in a sandbox.
A staging environment, essentially, so it can't touch the live system.
Right. Then the continual evaluator steps in. It takes this proposed new harness and runs it through a rigorous gauntlet before it ever sees the light of day.
What kind of gauntlet?
First, it checks if the new code actually solves the current problem. Second, it checks if it violates any core validity constraints like, system security.
Sure, that makes sense.
But crucially, the third step is testing the new harness against a historical anchor set.
Wait, explain the historical anchor set. What is that?
It is a curated library of previous tasks the agent has already mastered. The evaluator runs the new harness against this old test suite to ensure retention. It explicitly checks to make sure the agent can still retrieve historical financial data, even with its shiny new pop culture search tool.
It verifies the radio doesn't honk the horn.
Exactly. Only if the candidate harness passes all three of those checks does it get committed to the task interface and experience memory as the new live deployed state.
Oh, that's smart. It institutes an automated QA department for the AI. It forces the system to prove the update is a net positive.
Right.
But, all of this assumes the AI has access to its own harness code to rewrite it. What if we are dealing with a situation where the harness is fixed?
What do you mean?
Like, say I am using a massive proprietary enterprise harness and I just need to train my open source model to use it better. I can't just have it rewrite the enterprise code.
Right, right. That brings us to a completely different challenge, which is highlighted in the black box RL framework research.
Oh.
Modern harnesses, things like Claude Code or OpenClaw, are incredibly intricate. They have custom logic, sub-agent scheduling,
Yeah.
hidden prompts that the user never even sees.
Yeah.
To the language model trying to learn how to operate inside it, the harness is essentially a black box.
Hmm.
The model doesn't see the underlying Python code. It just sees the inputs it receives and the outputs it generates.
And historically, trying to use reinforcement learning RL to train a model on how to use a tool is incredibly difficult if the AI can't see the underlying mechanics of the environment, right?
It is a massive computational headache.
Yep.
I mean, if the interaction process is transparent and simple, reinforcement learning is straightforward. The model takes an action, gets a reward, and updates its weights.
Simple enough.
But when the harness has complex hidden logic, traditional RL frameworks struggle. The model might take an action that fails, but because the failure happened deep inside the hidden logic of the harness, the model has no idea why it failed.
It just knows it didn't work.
Exactly. So, researchers developed a brilliant workaround. They completely decoupled the policy optimization from the opaque harness.
How did they do that?
They placed a serving proxy right at the boundary between the model and the harness.
Here's where it gets really interesting. A proxy is just a middleman, right? So it's intercepting the communication.
That is its exact function, yeah.
Yeah.
The proxy intercepts every single call the model makes to the harness and every response the harness sends back.
Okay.
By recording just this boundary interaction, they can reconstruct the entire multi-turn interaction without ever needing to look inside the black box of the harness itself.
Okay, so it's like teaching someone to become a pro at a complex video game just by capturing their controller inputs and recording whether they lived or died on the screen.
Yes.
Like, without ever having to peek at the underlying game engine code. You don't need to know how the physics engine renders the jump. You just need to know that pressing A at this exact millisecond resulted in a successful jump.
That captures the essence perfectly. But the researchers took it a massive step further.
Oh.
Because these multi-turn interactions can be highly fragmented, like maybe the agent tries a web search tool, fails, goes back, tries a calculator, fails, goes back to a database.
Right.
Training a model on that linearly is incredibly inefficient. The model gets confused about which specific action caused the final failure.
It loses the thread.
Exactly. So the proxy organizes all these captured calls into what they call prefix trees.
Prefix trees. Wait, if it's organizing everything into a prefix tree, doesn't the model lose the context of the specific errors it made on the first branch? How does it learn from failure if the history is generalized into a tree?
It is actually the opposite. The tree structure gives it better context.
Really?
Yeah, imagine a conversation or a workflow as a branching tree. Instead of treating every single attempt as a separate isolated timeline where the model has to relearn the entire history from scratch, a prefix tree stores the shared history just once.
Oh, I see.
If the agent takes 5 successful steps down a path and then tries 3 different tools for the 6th step and 2 fail, 1 succeeds, the prefix tree maps that out as a trunk with 3 branches.
Okay, got it.
This allows the RL algorithm to optimize the model's choices over the entire tree structure simultaneously. It can see exactly where the branch diverged between success and failure, which makes the learning process wildly more efficient.
I see. It isolates the exact moment a good decision turned into a bad one.
Exactly.
Did this proxy method actually yield results?
It did. Testing the Quen330A3B model, they saw up to a 14.81-point improvement on the SWE-bench benchmark, which is a rigorous test for tool use.
Wow, that's huge.
But the most impressive part was that they successfully executed mixed harness training.
Mixed harness training, meaning training one model on multiple different harnesses at the same time.
Yes, because the proxy normalizes all the interactions into these prefix trees, it abstracts away the specific quirks of any single harness.
Oh, that's brilliant.
They could feed the model training data from completely heterogeneous harnesses like OpenClaw and Claude Code within the exact same training batch.
So it's not just learning one system.
Right, the model learned to generalize its tool use conventions. It learned the fundamental concepts of how to use software rather than overfitting to the specific buttons of one isolated environment.
That is incredibly clever. But, capturing all these prefix trees, running thousands of simulated interactions across different harnesses, that must require a supercomputer.
It usually does, yeah.
How does a normal startup or an academic lab actually afford the compute to do this kind of reinforcement learning?
Well, you've hit on the exact logistical nightmare of Agentic RL, and it is what our next paper, Agent Lightning version 1.0, aims to solve.
Okay, Agent Lightning.
Traditional RL frameworks often require you to implement your agent loop directly inside their heavy training framework. It's clunky, it's hard to integrate those black box harnesses we just talked about, and crucially, it leaves your expensive GPUs sitting idle half the time.
Wait, why are they sitting idle? If the system is training, shouldn't the GPUs be running at 100%?
You would think so, but reinforcement learning has two distinct phases. You have rollout and you have update.
Okay.
In the rollout phase, the model is exploring the environment, trying out tools, and generating data. This uses inference.
Right.
Then, in the update phase, the system calculates the rewards and updates the neural network weights. This uses training compute.
Ah, I see where this is going.
In traditional setups, while the model is out rolling out attempts in the environment, the heavy GPUs used for updating the weights are just waiting around doing nothing.
So you are paying thousands of dollars an hour for compute that is basically taking a coffee break while waiting for the model to finish its web search.
Exactly. And Agent Lightning fixes this with what they call collocated async RL.
Collocated async RL, how does that work?
Let's use an analogy. Imagine a restaurant kitchen. Traditional RL is like a chef who chops all the vegetables, and only when they are completely done chopping, they turn on the oven to preheat.
Right, so the oven sits idle while the chopping happens.
Collocated async RL is a chef who turns on the oven, and while it preheats, they chop the vegetables. Agent Lightning allows the rollout phase and the model update phase to timeshare a single pool of GPUs efficiently.
Oh, wow. So inference and training are happening simultaneously on the same hardware.
Yes!
That must be a massive piece of software to orchestrate all that timing.
That is the most shocking part. The entire Agent Lightning framework is only about 3,500 lines of code.
Are you serious?
It is incredibly lightweight.
Oh.
But with just 6,000 training examples, they use this tiny framework to improve a Quinn 3.59b model on the SWE-bench software engineering test from a 41.8% success rate to 56.4%.
Wow.
That is a massive 14.6% absolute gain in its ability to solve real-world GitHub issues.
For anyone listening who isn't a software engineer, 3,500 lines of code is basically a rounding error.
Yes.
A basic smartphone app has more code than that.
It really is tiny.
Is the big deal here just saving money on GPUs? Or does stripping a framework down to 3,500 lines of code offer something more fundamental for researchers?
If we connect this to the bigger picture, the fact that a framework this small can yield a 14% improvement on real-world coding tasks is staggering. It democratizes the whole space.
Yeah, because you don't need $100 million in compute anymore.
Exactly. It brings agent training out of the massive tech monopolies and into the hands of smaller teams.
So if we take a step back, we have a world where AI agents can rewrite their own operating systems to be more efficient. We have proxy frameworks teaching them how to master black box tools they can't even see. And we have lightweight, cheap training frameworks making all of this accessible to anyone with a decent computer.
It's moving very fast.
The capabilities are compounding at a ridiculous rate. Which brings us to the final and perhaps most vital question of this deep dive.
Right.
As these harnesses get infinitely more complex and capable, what are the security flaws?
Yeah, as the capabilities of these harnesses explode, the attack surface multiplies. And that is the focus of our final source, a comprehensive security benchmark called harness risk.
Harness risk, okay.
The researchers here recognize that we have been evaluating agents based on how well they complete a task, but we haven't been evaluating how safely they do it across their entire life cycle.
Okay, so they built a test for that.
They did. They built 128 sandboxed test cases spanning 6 distinct life cycle phases of a harness.
Walk me through those phases. Where does the life cycle start and end?
The 6 phases are harness configuration, capability extension, runtime operation, state persistence, action control, and incident recovery.
Okay.
The researchers tested 3 major agent harnesses, OpenClaw, Hermes, and Nanobot, across all these phases.
And how do they test them?
They did this by pairing a totally benign user objective with an adversarial instruction hidden inside a workflow artifact, like, an untrusted email, a corrupted calendar invite, or a web page the agent was asked to summarize.
For anyone listening who manages enterprise AI, this is your nightmare scenario.
Oh, absolutely.
Your employee asks the AI to summarize an email from a vendor, but the vendor has hidden invisible text in the email telling the AI to forward your internal documents. So, did the attacks actually work?
They worked alarmingly well.
Huh.
And this leads to the biggest finding of the harness risk paper. High task utility can completely mask unsafe execution.
So, what does this all mean? Does this mean an agent could flawlessly execute my command to refund a customer, but secretly exfiltrate my database to a hacker at the same time?
Yes. From the user's perspective, the agent did a perfect job. It summarized the email flawlessly. The utility score on the dashboard says 100%. High fives all around.
Right.
But in the background, because of how the harness handled the hidden instruction, the agent was successfully manipulated into bypassing a review process or quietly exporting a sensitive database.
Wow. Success is the ultimate camouflage. If the agent does its job, we don't check its pockets. Out of those 6 life cycle phases you mentioned, where are these systems the most vulnerable? I would assume it's during runtime operation, when it's actively reading the malicious email.
Interestingly, no. The most vulnerable phase across all the tested harnesses was actually harness configuration.
The setup phase, why?
Because this is where the initial policies, the API connectors, and the permission boundaries are set.
Oh, I see.
If an attacker can manipulate the configuration instructions, say through a malicious setup document or a compromised template that a developer downloads off the internet, they can fundamentally weaken the isolation of the agent before it even starts its first task.
So they aren't attacking the AI's logic, they are attacking the rules of the game.
Yes, they can expand the scope of its file access or configure a webhook that quietly copies all output data to an external server.
That's terrifying.
It's the highest risk because it sets the foundational rules for everything that follows. If the configuration is compromised, the runtime operation is doomed from the start.
The paper also highlighted a specific quirk with one of the harnesses, the nanobot harness, I think, regarding how it handles memory. Can you explain the mechanics of what happened there?
Yeah, this is a fascinating failure mode in the state persistence phase.
Okay.
Nanobot has a long-term memory feature designed to make the agent smarter over time. During testing, they found instances where an agent encountered a poisoned piece of data or a malicious rule during a transient temporary task.
Like reading a sketchy web page.
Right. But the harness, trying to be helpful and learn from its experience, summarized that malicious instruction and wrote it into its long-term durable memory.
Oh no. So it's not just a one-time hack. The agent actually internalizes the virus as a core belief.
Exactly. It effectively turns a transient one-off attack into a permanent trusted rule.
Wow.
The next time the agent boots up to do a completely different secure task, it consults its memory. It reads the poisoned rule it saved yesterday, assumes it is a legitimate system instruction because it came from its own internal memory drive, and it auto-approves an action it shouldn't.
That is wild.
It really highlights how incredibly dangerous durable memory can be in a harness if you don't preserve the authorization context. Meaning, the AI needs to remember where it learned a fact so it knows whether to trust it later.
Wow. Let's take a breath and pull all of this together. The trajectory we've mapped out today is just staggering.
It really is.
We started with models acting as their own software engineers, evolving their own code to get better at tasks, but requiring guarded sandboxes to ensure they don't overwrite their own core competencies. That was SWE-bench and HCL. Then we looked at how proxy systems and prefix trees allow models to map and master completely opaque black box tools. We saw how agent lightning collocated async RL shrinks the immense compute costs of this training down to a lightweight framework anyone can use.
Yeah.
And finally, harness risk showed us the dark side of this autonomy, how high task success can mask deep security breaches, especially when vulnerabilities creep into configuration files or get permanently encoded into an agent's long-term memory.
When you look at all 5 of these papers in aggregate, the takeaway is pretty clear. The future of being truly well-informed in the tech space isn't just about tracking which foundational model has the most parameters or scores highest on a standardized test.
Right.
It's about understanding this invisible scaffolding. It is the harness that dictates how that raw intelligence is actually wielded, how it learns from its environment, and how it might be quietly compromised without us ever noticing.
It really is the steering wheel, the brakes, and the GPS, not just the engine.
Exactly. And I want to leave everyone listening with a final thought to mull over that kind of connects all of these threads.
Okay, let's hear it.
We now know that agents can evolve their own harnesses to be more efficient. We also know they're learning to navigate entirely black box tools through reinforcement learning.
Right.
So how long until a model evolves a harness that is so incredibly complex, so highly custom tailored by the AI itself, that no human auditor can even understand its configuration files?
Oh.
And if we can't understand its configuration, how do we check for the very security risks we just talked about?
Hmm.
Ultimately, who audits the harness when the harness builds itself?
That is a brilliant and honestly slightly terrifying question to end on. If the AI is writing its own rules, we might not even know how to read them. Thank you for joining us on this deep dive. Keep questioning the scaffolding around the systems you use every day, and we'll see you next time.